Talked about addition and subtraction of vectors. We also need to talk about how to multiply vectors together, and that gets a little bit more complicated. Before we dive into that, I just want to be very straightforward. There is no such thing as division of vectors. So subtraction undoes addition, peachy, that's all good. For ordinary numbers and for lots of other things you're used to thinking of, division is the thing that undoes multiplication. But when we talk about vectors as mathematical quantities, there is no such thing as division by a vector. I can't divide by the direction north. That has no meaning. So I can do lots of things with vectors, but if you come to a point in your solution where you divide by a vector, you are off the grid. You are just way, way off the map. There is no definition for how to even conceive of doing that operation. Um, so that is one of the things to be cognizant of as you're working with vectors. Add and subtract, that's peachy, intuitive. Multiplication gets a little bit more complicated, and we have some different uses of multiplication to do specific things. And then division is just a no-go. All right. If we're talking about ordinary numbers, so like A is 3 and B is 2, we could write out how we want to make the product 3 times 2 equals 6 lots of different ways. Like you had a multiplication sign. Let's find that on your calculator. It's a little bit more subtle. You can just put a dot. That also means multiplication for numbers. And then eventually you learned, oh, I could just write them next to each other, perhaps in parentheses, perhaps not. So 3, 2, if there's nothing else there, it's an implied multiplication. So all of those mean the same thing. If A is 3 and B is 2, those all give me 6. All right. When we talk about vectors, that is no longer true. For ordinary numbers, this is like apple, 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 all apple. When we talk about doing this with vectors, they're not the same thing. We're talking about like rock, potato, elephant, completely different stuff. All right. In this class, we're going to need the last two, as we'll learn that's a vector dot product and a vector cross product. A, B, just next to each other, implied multiplication. That exists as a mathematical operation. It's called the outer product or the tensor product. We won't need that for this class. But we will use the other two, and there's another way of multiplying a vector that we're going to need. So we're going to, in this video, we're going to learn about 3 ways to multiply vectors, what those mean, how to perform those operations. All right, so the first one is rescaling a vector. We've actually done that already. We didn't highlight it at the time. We didn't make it like a big whoop-de-doo deal. But if I take some vector and I multiply it by a scalar, then you've rescaled the vector. And this is how we made the vector minus a out of the vector a. That was multiplying by the scalar minus 1. All right, so that is easy enough to do, and it's so easy to do that we didn't even notice that we did it. All right, the next one is goes by a couple names, and I will probably unfortunately use these interchangeably. The scalar product or the dot product, which is defined as vector A dot vector B. So we'll learn how to compute it in a little bit and some consequences of it. But I want to start off with what good is the dot product? What is it trying to do for you? So I take my 2 vectors that I want to form the scalar product of, A and B. I put them tail to tail. And then the scalar product is telling me how much of the vector A points along the vector B, or conversely, because it commutes, how much of the vector B points along the direction A. So how much of A points along B? Let me sketch in here a perpendicular. So this is dropping a perpendicular from the vector A to B. So how much of A points along B? Well, it's going to be this much, right? And so the scalar product is going to give me an answer back, which is the length of this vector. Okay. How much of A points along B? And I will get the very, very same answer if instead we go the other way. So instead, let's drop a perpendicular from B to the vector A. So, oops. And all right, so there's my perpendicular dropped from B to the vector A. So I will get the very same answer for the length of this vector, which is how much of the vector B points along the direction of the vector A. Okay. And obviously, if the two vectors are parallel to one another, then all of them point along the direction of the other one. All right. So this gives us our first way of thinking about how to compute A dot B. I take the magnitude of the vector A, multiply it by the magnitude of the vector B, and then it is the cosine of this angle phi. And phi is the smallest angle between the directions A and B. There's a longer angle as well if I went around the other way to get 360 minus phi, but that's not what we want. So how much of A points along B? Magnitude of A, magnitude of B times the cosine of phi. And phi is this angle. Okay. If you have the Cartesian components of A and B, then the dot product A dot B is also equal to the sum of the components products. So A dot B would equal AX times BX plus AY times BY plus AZ times BZ. And if it were some n-dimensional vector beyond 3, I would just keep adding those in as well. So either of those two methods are perfectly fine for how to compute the value of A dot B as vectors. And whichever one you use is whichever one is going to be easier for the task at hand. I could just use their magnitudes times the cosine and the angle in between them. And sometimes this could be a useful way to get the angle between two vectors. Or I could do it in terms of the sum of the products of their components, component-wise. All right. Since this is asking the question, how much of A points along B, if A and B are perpendicular to each other, then the answer is 0. If A and B are perpendicular, then none of B points along A, so A dot B vanishes. All right, so let's go through some practice with the scalar product, dot product. There are two vectors shown, A and B. Complete the following statement. The component of vector A along vector B is, which of those do you think is correct? So think about it, talk about it with your physics neighbor or neighbors, and then when you're ready to go on, unpause the video. All right. So the component of vector A along vector B is smaller than the magnitude of vector B, which is just B without the arrow. So if I draw in my perpendicular, I drop the perpendicular from A vector to B, then we're saying this side, the triangle, right? Okay, that is shorter than the magnitude of B. So fairly straightforward. All right, let's try another one. What is the scalar product A dot B if A is 1.1 I hat plus 2 j hat? So 1.1 along the x direction plus 2 along the y direction. And the vector B is 1 I hat minus 1 j hat. So the vector b points 1 along the x direction and minus 1 along the y direction. So what is the scalar product a dot b? Work that out, and then when you have compared answers with your physics neighbors, you're ready to proceed. Go ahead and unpause the video. So first off, should be apparent to you that C and D are just not possible because we're using the scalar product. The answer has got to be a scalar. And this is a vector for C, and choice E, that's also a vector. Okay, so you can't pick a vector to be a scalar. All right, so then we're doing this component wise. So 1.1 times 1 is 1.1, and 2 times minus 1 is minus 2. So 1.1 minus 2 is minus 0.9. So it's using our second way of calculating the scalar product since we are given the components. All right. Next question. Scalar product of two vectors a dot b can be determined in a variety of ways. Which one of the following choices is false? So read through all those choices. One of them is incorrect. Once you think you have it sussed out and figured out, confer with your physics friends, and then you can unpause the video. All right, so choices that are true is a dot b is the magnitude of a times the magnitude of b times cosine of theta. Theta is the smallest angle between the two vectors. That works. Scalar product is the product of the magnitude b and the component of the vector a in the direction of vector b. That works. The scalar product of these two vectors could be equal to 0. Absolutely could if they are perpendicular to each other. The scalar product is a product of the magnitude a and the component of the vector b in the direction of a. Yes, absolutely. The one that is false, because it's sort of the opposite of choice A, the scalar product is equal to the product of the magnitudes of the two vectors and the sine of the smallest angle between the two vectors. That is false because it is not the sine, it is the cosine. And more on that next. All right. The last way to multiply vectors together that we're going to need is referred to as the vector product or the cross product, or some people, and I think it's actually more of a European thing, call it the wedge product. The point of this vector product is construct a direction that is perpendicular to two other directions. So given two vectors, what is the direction, or what is the vector that is perpendicular to both of them? Which is it's a very useful thing for describing laws of nature in terms of things that will come up in physics. Right. We'll use the vector cross product when we talk about angular momentum, or further afield when you talk about magnetic fields. All right, so the notation for this is it's a vector product, so the answer is a vector. So the vector C is equal to the cross product or vector product of A cross B. And then there are two steps to this. The first thing is, what's the magnitude? The magnitude of the answer C is going to be given by magnitude of A times the magnitude of B times the sine of the smallest angle in between the two vectors. So again, you put the two vectors tail to tail. A and B are tail to tail. Measure off the angle phi, and then the magnitude of their vector product will be magnitude of A times the magnitude of B times the sine of the angle phi. The direction, because this is a vector, C is a vector, it needs to have a direction as well. This follows from what is called the right-hand rule. And we're not going to need this right away in the class, but we will need this when we get to angular momentum and torque. So once we get to rotations is when we're going to be flirting around with the vector cross product. All right, so the idea to get the direction, take your right hand, okay, align the figures of your right hand with the first vector. So that's for A and A cross B like that. And then I want to be able to sweep the fingers of my right hand so that they're parallel to the direction of the second vector. So I have to rotate my hand like this so I can curl them like that. And then the thumb is coming out of the plane of the page. Okay, because this works because your fingers can only bend in one direction. That's how the right hand rule is working. So I go from A, curl into B, and the thumb of my right hand is coming out of the plane of the screen. So for A cross B, I would be getting an answer that is coming out of the plane of the screen or out of the plane of the page. And you can verify for yourself if you reverse the roles of A and B, you get a vector that points in the opposite direction. So that would be into the plane of the page. All right, so some things to note about the vector product. So by construction, the vector that's the result, C, is perpendicular to both A and B. And the vector product will exist as long as there is a unique direction that's perpendicular to both A and B. If A and B point along the same direction, they're parallel, there's an infinite number of directions, and so there's no unique answer. So the cross product vanishes. And then the same thing if A and B point in opposite directions. There is no unique direction that is perpendicular to both A and B, and then the vector cross product will vanish. The order matters, so it does not commute. The vector product does not commute. So if B cross A points in a particular direction, A cross B points in the opposite direction. Okay, so the dot product we saw commuted, the cross product does not. All right, there is a big long formula here on the slide. If you ever in this class need to sit down and figure out a vector product in its full three-dimensional glory, come and apply this formula. There's actually an easier way to do this, but it's in terms of a tensor, and I promise you we wouldn't use tensors. So there's an easier way of doing this in terms of what's called the Levi-Civita symbol, which is the totally anti-symmetric tensor, but we're not going to use that for this class. So if you ever happen to need it, this is in your textbook, or you can refer back to this part. And you basically just plug in the components and you get the X, Y, and Z component of the resulting vector from the vector product. So the X component of that new vector is made out of the Y and Z components of A and B. The Y component is made out of the X and the Z components of A and B. And the Z component is made out of the X and Y components of A and B. All right, so multiplication of vectors, we can rescale a vector, which could make it longer or shorter or reverse its direction. We can do the vector, the scalar product, or also known as the dot product, which is asking the question, how much of A points along B? And then we can do the vector product, also called the cross product, which is construct a vector that is perpendicular to both A and B. So if C is equal to A cross B, then we can find the magnitude of C as the magnitude of A times the magnitude of B times the sine of phi. And then the direction of the vector C, the direction it points, follows from the right-hand rule. All right. And so we have rescaling, which is a scalar times a vector gives a vector. We have the scalar product, which is vector dot vector gives a scalar. And then we have the vector cross product, which is a vector cross vector gives another vector. We need to keep those straight about which operation produces a scalar, which produces a vector. And we need to keep that straight because no scalar on its own can be a vector, right? Vectors are combinations of multiple components. All right. So for the vector cross product, there are pairs of vectors, choices A, B, C, D, and E. The cross product of which pair of these vectors is equal to 0. Which is intuition, looking at them, which one of these have to have a vector cross product that vanishes. So think about what you think the answer is, and then compare with your physics neighbor. And then when you guys are ready to move on to the solution, go ahead and unpause the video. All right, so for the pair of vectors in D, they're pointing in opposite directions. So there is no unique direction that's perpendicular to both. So therefore, the vector cross product will vanish. A, B, C, and E will all have an answer that is non-zero for the vector product. All right, last question. So it's a little check to make sure we're all clear on notation. Doing all sorts of things with vectors here. You have 5 different choices. These are all vector operations because they're operating on vectors. But which out of these 5 will produce a vector? And we're given the constraint that the magnitude of A and the magnitude of B and the magnitude of C, magnitude of D are all non-zero. So you're not trivially saying, well, if the magnitude of B happens to be 0, then it's 0. No, this is which out of these 5 potentially valid expressions multiplying vectors together is going to give you an answer that is itself a vector. So think through the 3 ways that we learned how to multiply vectors together, talk about it with your neighbors, and then let's see if we come to the right conclusion. All right, so let's go through these one by one. So B cross C is a vector, and then a vector dotted with a vector is a scalar. So A is a number, it's a scalar. A dot B, scalar product, obviously a scalar. C minus B is some other vector. Vector dotted with a vector is a scalar. For choice in D, A dot B is a scalar, but then that scalar is multiplying a vector. So this is like our first way of multiplying vectors. I am multiplying a vector by a scalar, which gives me a vector. All right, E, I've got A cross B, which is a vector. C cross D is another vector. So I have vector dot vector is a scalar. So out of these, A, B, C, and E are all just numbers, or just a scalar. D is giving me a new vector. All right.